So by this point, you've seen a number of functions and you've seen their graphs. And in particular, we've seen some parent functions. And we know what they look like. We know the basic behavior of the functions. But let's suppose we want to move those functions around. We want to raise them up, lower them, stretch them out vertically and horizontally, maybe shrink them. Well, how do we do that? That's what we're going to look at with this video, transformations. We're going to look, first of all, at rigid transformations. That's where we take the graph and we move it. We don't change the shape of it. We just carefully pick it up and move it or flip it. In particular, we're going to look at vertical transformations, moving graphs up and down, horizontal, moving them left and right, and reflections, maybe reflecting them across an axis. So let's start with a vertical shift. Now, what we'll, I want to think back to this parent function, f of x equals the absolute value of x. And remember, that function looks like this. It's just, a v. And what we want to do is we want to determine, well, what happens if we add a 5 or just add some number to the function? In other words, like absolute value of x plus 5, or subtract the number from it. So let's look at this. Here is the absolute value function. We put in a -3, we get out of 3. Put in a -2, we get out of 2, and so forth. These are ordered pairs for the absolute value function. Now, what happens if we add 5? Instead of the absolute value of x, let's suppose we have the absolute value of x plus 5. Well, here's what we got then. And notice that when we add 5, notice we've got the same x's over here that we looked at over here, but notice that all the y's are of course increased by 5. That's just obvious. That happens, right? So you take the absolute value of -3, add a 5 to it, you get an 8. So all the y values are increased by 5. Now what happens if we subtract 5? Well, same thing, except the action is on the y's. The y's are decreased by 5. Notice, here we had 3 plus 5, here we have 3 minus 5. So what this does, subtracting a 5, means all the y coordinates are decreased by 5. So the -3, 3, that point becomes a -3, -2, and so forth. So let's look at the graph then. So if we go through and we plot all these points, and get the absolute value graph, and then we come back and we look at the graph where we didn't just have the absolute value, we had the absolute value of x plus 5, and we plot those points. Notice everything is raised up 5. If we plot all these points, it's as though we just took all these blue circles and raised them up 5, made the yellow circles. See, so the effect that adding that 5 had on the graph was to raise it up. So if we want to raise a function up, what we need to do is add to it. So, for example, this absolute value of x plus 5, it's going to do this. It's going to raise the graph up 5 units. So here's the graph. The graph is normally down here with the vertex at the origin. Now it's raised up 5 units. This is a rigid vertical shift. So if we subtract 5, we get this. Okay, it lowers it 5 units. Now, in general, if we have a graph and we want to raise it up, let's suppose this is f of x. We want to raise that graph up a certain amount or lower it down. If we want to raise it up, we just add a number to it. And it raises it up. There it is. That's f of x plus k. Now notice the shape of the graph did not change. It's the same graph, only at a different location. So here's the thing. If you have f of x plus k, and k is positive, then the graph is shifted up k units. Or another way to say that, each y value is increased by k units. Now on the other hand, if you have f of x minus k, where k is positive, then the graph is shifted down k units, and each y value is decreased by k units. That's another way to say it. So that's how we can, without changing the shape of the graph, we can raise it up or lower it down. Now let's talk about a horizontal shift. So let's consider this absolute value function and think about what would happen if we add 5 inside the absolute value with the x, like this. So we have the absolute value of x plus 5, that quantity, instead of the absolute value of x, close absolute value plus 5. So now this is a little less intuitive, but think about this. Think about if we want to get the same y values, what do we need to do? What kind of x values do we need? In other words, to get the 2, we needed to put in a negative 2. What do we need to do in this situation if we're adding 5 to that value that we put in? Well, we've got to counteract the 5, right? So I can't just put in a negative 2 because I would have negative 2 plus 5 and I would get a 3. If I want to get this 2, I've got to counteract that 5. So here's what's going to happen. We've got this negative 2. We're going to subtract 5. In other words, I'm having to move 5 to the left to get the same y value. So notice, negative 2 minus 5, that's negative 7. And now, if I put in a negative 7 in here, I get negative 7 plus 5, and I get a 2. See? If I put in the negative 7. Now, let's look at this. Negative 1, we subtract 5, we get negative 6. Negative 6 is what we've got to put in here to get the negative 1. Absolute value of negative 1 is 1. So you can see the way this game is played. What we're having to do is counteract this plus 5 that's been put in here with the x by moving to the left 5 units. Okay, so let's look at the graph. Here's the graph of the absolute value of x. Now, let's suppose we want to look at this one. Let's plot these points here. Negative 7, 2. These are points we found on the previous slide. If I plot these points, you notice that what happens is our graph has been shifted to the left because every point we had to move to the left 5 units to overcome that plus 5 that was added in there. So let's look at this. We've got this ordinary, just a random function here, and we want to add some number. Let's suppose k is positive. What happens then? We move k units to the left. Now, if that were x minus k, we would move k units to the right. So here's the deal. F of x plus k, if k is positive, the graph is shifted to the left k units. Or another way to say that is each x value is decreased by k units. So you're doing the opposite, right? If it's inside with the x, the action is on the x, but it's the opposite. Now we have f of x minus k. K is greater than 0. The graph is shifted to the right k units. Or in other words, each x value is increased by k units. Now let's take a look at reflections. Okay? Let's just suppose this is negative f of x. I've got k in there, but that's not going to matter right now. What we're just looking at now are reflections. So, first of all, reflection in the x-axis. Let's consider the function, the absolute value of x. And we know what this graph looks like. We've looked at it several times. It's a good one to explore these transformations. Now, let's suppose I've got negative absolute value of x. Well, if I put in a negative 2, take the absolute value of it, I get a 2, but then I multiply by negative, right? I've got the negative in front of it. I get a negative 2. So if you notice what happens is every value I get, I'm going to take the opposite of it. Well, if you think about the effect that would have on the graph, it's going to just flip it in the x, over the x-axis, right? Every positive x value, every positive y value becomes negative. Now, if we had negative y values, they would become positive. Everything is flipped. So it turned that graph upside down is what happened. Now, let's look at a reflection in the y-axis. And to do that, we'll change over to the square root function. Let's suppose that we've got f of x equals the absolute value of x. Now, f of negative x would be negative absolute value of x. So, in other words, I'm looking at seeing, well, what happens when we have the absolute value of negative x versus the absolute value of x? Well, okay, here's x. Here's the square root of, I may have said absolute value, I meant the square root. Sorry about that. So, here we have this. I'm going to put in these x values, and you can see the corresponding y values. Now, over here, notice that I can't put in these same x values into the negative x, right? Because what would happen is I would be trying to take the square root of a negative number. So what I'm going to do is, to get these same y values, what do I have to do? Well, I need to take the opposite of all the x's. In other words, I'm going to, instead of plugging in 1 to get the square root of 1 is 1, I'll plug in a negative 1. And notice, the square root of negative 1 is 1. See? So in other words, I had to compensate for this negative that's in there. To get the same y values, I had to go across the y-axis. To get a 1 for my output, I had to go over to negative 1 and plug that in. To get the 2 for an output, I had to go to negative 4 to plug in. I'm having to compensate for the fact that I have a negative here. So let's see how this works. Let's plot these points, the square root function. Okay, here it is. We're just plotting some points. And now let's look at the corresponding changes we had to make to get the same y values. In other words, I have the same y values, but notice I had to go across the axis. So I still get the positive 1 here, but I had to get that from plugging in the negative 1. And you can see how this goes. So this graph has been reflected in the y. So now let's transition over. We've looked at rigid shifts. Now let's just quickly look at non-rigid shifts. We're going to look at vertical, horizontal. But first of all, I want to take a look at the vertical. Okay. And once again, I'll start with this absolute value function. We know what the absolute value function looks like. Now, let's suppose instead of absolute value of x, I say 3 absolute value of x. Well, notice what that does. Every output gets multiplied by 3. So we get these points. Everything is multiplied by 3, and what it does is it kind of stretches the graph out vertically. So when I put in a negative 2, instead of getting out a 2, I get out a 6. Instead of getting when I put in a negative 1, instead of getting a 1, I get a 3. See, it just, every x value gives you a greater y value output. So here's a little picture of how it looks. Notice, here's the absolute value of x, 2 absolute value of x, 1/2 absolute value of x. You notice the 1/2 flattens it out. So this is a non-rigid shift. Okay, so the actual shape of the graph has changed a little bit. It's gotten taller, skinnier, shorter, fatter. Okay, so here's the comparison there. That's what happens when you multiply the outside of the function. Now let's look at this. Here we've got a function here, and we want to do k times f of x, it's going to stretch it out if k is bigger than 0. Okay? Or if k is bigger than 1. Yeah, k is bigger than 1. If k is less than 1, between 0 and 1, it would tend to flatten the graph out. Okay, so here we go. We've got k f of x, and the absolute value of k is bigger than 1. And this is a vertical stretch. Now, if the absolute value of k is less than 1, now remember, if k is negative, it's going to flip the graph. But we're just talking about stretches here. So if k is less than 1 in absolute value, in other words, if we have like 0.5 f of x, that would be a vertical shrink. It would kind of smash the graph down. If it's bigger than 1, like 5, it's going to stretch the graph up. Okay? So each value, the bottom line is each value, y value, is multiplied by k. And that's how you get your new y value. So we've got these non-rigid shifts. We've got vertical, and now we'll look at horizontal. Okay? So here's the absolute value of x. We know what this looks like. Now let's look at what happens when we put a 2 inside the absolute value. Now, we want to find the x values that yield the same y values. Now, it's inside the function this time. So we've got to compensate for the fact that when we put an x in here, it gets multiplied by 2. So what we need to do is divide every x value over here by 2. So -4 divided by 2 is -2. That's what I put in here. Now, the absolute value of 2 times -2, that's 4. Okay, so the absolute value of -4. And we do that to all of these. For the -2 divided by 2 is -1. 2 times -1 is -2. Absolute value is 2. We do this to all of these. Now, this is how we deal with something inside the function multiplying. Okay? And we can graph these, and we have here an action on the horizontal. Now notice, if it's inside the function, you're going to do the opposite to the x's. If it's outside the function, like 2, absolute value of x, we multiply all the y's by 2. If it's absolute value 2x, we divide all the x's by 2. Okay? So let's see how this would look. We've got f of x. Here's just a general function. We've got f of kx. And it's going to be an action. In this case, it looks like the graph has been compressed, right? Okay. So the action is on the x's. So here's what we've got. If the absolute value of k is bigger than 1, we've got a horizontal shrink. You think of it causes things to happen faster. We get the y values faster. Okay? If it's less than 1, it's a horizontal stretch. It takes longer to get the same y values as the original function. So if we had f of x, it's going to take longer if the absolute value of k is less than 1. Like f of x, things are going to happen one rate, but f of 1/2 x, it's going to take twice as long. Okay. Okay. So there's your non-rigid horizontal. Each x value is divided by k. That's how you can compute the corresponding ordered pairs. So transformations, we've got rigid. Okay, we've got horizontal, we've got vertical. We've got reflections. We've got reflections in the x-axis, reflections in the y-axis. And now, here are these transformations. We've got non-rigid, we've got the horizontal non-rigid, the vertical non-rigid, and then we've got the stretching and the shrinking. Okay? So we can stretch and shrink horizontally or vertically.